Alright, so in this video we're going to be going over how to insert into a binary search tree. So one of the features of a binary search tree that is very nice is that whenever you add a new node, they're always inserted at the bottom. And so they always become a new leaf. And so that really simplifies the amount of things that you have to reconnect when insert happens. So the basic algorithm is that you start by searching the tree, which we already went over. And if you find a key, then you return, or you handle that case somehow. But generally, you don't allow there to be duplicates, right? You can only have one instance of the key. The key has to be unique. So you're not going to ever insert twice. So as you know, with the C++ implementation, you could also have it replace it, but you never insert twice. And so generally speaking, we're going to say you return. If you don't find it, then you basically insert a new node where you fell out of the tree, which is that really nice feature of like adding at the bottom as a leaf. So let's look at it with an example. So again, pointing out this tool here, which is really nice for a lot of the binary search tree visualization and drawing out of binary search trees. So let's say that we wanted to insert 4. So we already know what the search algorithm is, so we're going to follow it first. So we start with 22. 44 is greater than 22, so we're going to go right. 44 is less than 49, so we're going to go left. 44 is greater than 35, so we're going to go right. And then 44 is greater than 41, so we're going to go left, and we're going to reach a null pointer, which means that we have fallen out of the tree. Now that we've fallen out of the tree, we are basically going to create a new node. We are going to fill it with the value of 44, and we are going to connect the parent of the node that we just fell out of, which we'll have to keep track of, and connect everything up. We'll also have to make sure that we initialize the children of the node that we just created with its children, which should both be null pointers. So we're just going to go through that algorithm in code and look at what that looks like. So let's write some pseudocode. Step 1 is we're going to search for the key, and like I said, we're going to return if you find the key, since we're not going to allow duplicates, and we're not going to allow replace. Step 2 is if it's not found, insert where we fell out of the tree. And then step 3 is we need to update the size because we just added a node, and we need to return out of the insert function. So let's go through each of those steps. So first, like we did last time for search, what's the coding pattern for insert? Go ahead and pause the video, think about it, and then come back when you're ready. So for search, we didn't need to keep track of a prev pointer. A cur pointer would do. But because we have to sync, because we fall out of the tree, so we go all the way down to the null pointer till we fall out, our cur is now going to be pointing to a null pointer, right? So in order to be able to link back to its parent, we're going to have to keep track of the node that we came from. So the answer here is that the coding pattern is that we're going to want to keep track of both the prev and the current node for insert versus for search when you only needed cur. So let's go over step 1. So step 1 should look very familiar. The only difference is that we're going to add a prev pointer. So this is going to become useful after we move into step 2 as well, but prev is going to be initialized to a null pointer. This is important actually. Having it initialized to a null pointer will help us better determine what cases we're under after we get out of step 1. And then cur is going to be that pointer that we move around through the tree. And prev will always be the parent of cur, except for at the beginning when it's null. So we're going to search. We're basically going to do that same pattern we used for search. We're going to compare the key that we're looking for with the actual key of the node, and if it's the same, we have found it. So we can return out because we don't want any duplicates. If the key is less than the node's key, then we're going to go left, and if it's greater, we're going to go right, which is the only case left. Now the only difference of this insert search versus the original search is, again, before we update cur, we're making a copy of it and saving that copy to prev. That way we always have the parent and the child as we walk through the tree. So then once we get down here and cur is equal to that null pointer, prev will always equal the parent. Step 2 is if we fell out of the tree, that means that we didn't find it, and we know that because cur will equal null pointer, and so we need to insert the new node. Sorry. Just like with linked lists, we're going to allocate our nodes on the heap, calling the new keyword, and this will create a memory for the node, and then we need to fill in all of its values. So there's a little bit more to fill in because there's more member variables of the struct. So we need to set its key. The key is going to be whatever we're inserting because we already found where it should go, so that's what that value is going to be. And then we know that all inserted nodes of a binary search tree are leaves, and so they have no children. So you can right away set those nodes to null pointers. This is really important, right? You can't forget to do this because all the algorithms depend on the children all pointing to null. If you don't, then insert won't work, right? Because you're assuming that once you've reached null pointers, then you know that you're at a leaf. So if you don't put those in there at this step, basically nothing else is going to work. So that just creates the node. So we're basically at a point right here where we've created 44, we've filled in its value, and we've filled in its children's pointers. But we need to connect it. So this step is a little tricky. Is how do we link this? So here's a couple of options. So go ahead and read these options, pause the video, and think about which option is going to work for us. Okay, so let's first start with C here. So C says if cur equals null pointer, then set the root equal to n. So this appears to be making a case for inserting the first node into the tree. However, cur, if you get to this stage of your code, cur is always null pointer, right? It doesn't matter if it's an empty tree or a tree full of nodes. Cur, in order to leave that initial loop during search, has to be null pointer. So this is not the right idea at all because cur is always null pointer at this point of the algorithm. But handling the case of a empty tree is important, and you always have to consider that, and it always requires you pretty much to think about what special case you need to consider. So this case here says, okay, if the key is less than the previous value, then you're going to insert it on prev's left. If the key is greater than the prev's value, then you're going to insert it on the right. That looks fine. Those are all fine things to do. But then it says otherwise, set the root equal to n. So it has the right idea, but the problem here is that if prev is null, which is what the case will be if you have an empty tree. So let's go back to search step. So with this search, we're initializing prev to null pointer. So if the root is null, which is what an empty tree would be, this loop doesn't run, right? Which means prev will be null pointer. So in the case of an empty tree, this is not going to work because it's going to try to dereference a pointer that's null. So this case doesn't work because prev could equal null pointer. for an empty tree. So, in order to handle the case of an empty tree, you're going to want to do this. Prev will tell you that. So if that while loop never happens, then prev never gets set to anything else. And so if prev is null, then you know that there is no new node to insert. There is just a new node to create and sync up to the root. So all you have to do is you created the node here, you need to set its root equal to that, and you're done. Otherwise, as long as that's not the case, that means you've fallen out of the tree because prev got set to something, and you basically just need to check if you should go to the left or the right of prev, and that's all this will do here. So here, with our example of 44, remember we created it. 44 is well, that's what key is. And then this is prev. So prev is 41. So this one says, is key 44 less than prev, which is 41? Which is false because 44 is not less than 41. So we're going to go into the else, which says set prev's right equal to the end node. So this is prev's right, and so that will get linked like that. So the whole algorithm with step 1 on a previous slide, it doesn't really fit on one slide. So step 1 is on a previous slide, and then step 2 and step 3 are completed on this slide, is shown here. This is what we just went over. You create the new node. Here you handle both an empty tree and where to link it up if it's not empty. And then here you've successfully added and linked it to the tree, so you're just going to update the size and you're going to run a return out of the function. So that is it for insert into a binary search tree. Thanks.